So I was saying that the second lecture is going to be more concepts and concepts that are new to you, and it's going to be a bit more challenging than the first. That was a bit of a summary introduction lecture, right? So in this second lecture, we're going to see several concepts, but first we can go through the concepts that you saw the other day. Just super quickly again, land atmospheric interface. You have land and the atmosphere connected by fluxes of water, heat, and chemical components. Those biochemical cycles, the one that we focus on the most is CO2. We have, and we saw it the other day, a connection between this water, heat, and carbon cycles in the Earth system, the climate system. We have a balance in the carbon cycle at land and the atmosphere through the photosynthesis and respiration fluxes, right? Photosynthesis taking CO2, respiration releasing CO2 into the atmosphere. We have transpiration as a flux of water, which is in fact kind of like a byproduct of photosynthesis, because plants, as we mentioned the other day, they try to capture CO2 from the atmosphere and they lose water through transpiration. But the reason they transpire is because they want to capture that CO2 from the atmosphere, right? So transpiration is an evaporation flux, a change of phase from liquid to gas, right? And is a byproduct of photosynthesis, the way we saw it the other day. Is the most important component of terrestrial evaporation, verdamping, I think you call it in Dutch, right? The second most important is, well, actually you have a tie in there, it depends on which ecosystem, but either interception loss or terrestrial evaporation. I think the other day I mentioned interception loss, and some of you didn't know what the concept was. So interception loss, or rainfall interception, is the water that rains, the precipitation that is captured, usually by vegetation, and then stays on top of vegetation and gets evaporated back into the atmosphere. It's not transpiration, because it's not water taken by the roots and then evaporated from within, inside the leaves, but it's actually water that stays on top of the leaves when it rains and then it's evaporated back. And it is quite important because first it's a loss of water, as I said, interception loss. The reason why I call it loss is because it never reaches the ground. So it's not accessible for plants, it's not accessible for humans, it doesn't recharge our aquifers, it doesn't flow through our rivers. It's just a loss, it's just a fraction of precipitation that never happens, really, right? And it can be quite high in forests. It can be like 25% of rainfall. So 1/4 of the rainfall in forests is just not even reaching the ground. So that is a very important flux in terms of the percentage of evaporation in a forest. It can be like 40%, 25% of rainfall, 40% evaporation. You know that evaporation has to be lower than precipitation of the land, right? And that's the reason we have rivers. So transpiration, very important concept. It's part of the evaporation from land, as I said before. The most important component, about 60 to 70% of all the evaporation that happens over the continents is transpiration. You have like 10% that is bare soil evaporation, so the evaporation that happens from the soil towards directly, and about 10% as well comes from interception loss, then 15%. Okay, so latent and sensible heat fluxes, super important for this course. We'll go through that a bit briefly as well in the lecture today, but we will certainly see them in following lectures. So we said the latent heat is just the amount of energy used to vaporize water, or for instance, melt water if it was from solid to liquid. In nature, it's evaporated water, usually what happens, right? At least in here. So you have that being the latent heat. The latent heat flux is just the latent heat, so the energy used to evaporate times the amount of water that is evaporating. So it's total energy that is used to evaporate. So it's like evaporation, but in units of energy. So latent heat flux and evaporation, same thing, just different units. One is a volume of water, the other one is an amount of energy. Sensible heat flux, on the other hand, is the warming sensible heat flux. So if you have, for instance, the surface sensible heat flux, that will be the amount of radiation that is here available to either evaporate water or warm up the atmosphere. The part that is going to warm up the atmosphere, that's the sensible heat flux. And the way it works is you have your radiation warming up the land, and the land is getting warm, so it conducts heat to the top atmosphere, right? So it's just conduction, it's just transfer of heat from the high to the low temperature through a gradient, right? And once that thin layer of air on top of the atmosphere is warmed up, because it's lighter, it moves up through convection in the atmosphere. So the sensible heat flux happens first through conduction from the solid to the gas, and then through convection moving together with the gas in the atmosphere. All that is a sensible heat flux. Likewise, actually, the latent heat flux, the way it works is you have that available energy, you use it to vaporize the water, that water gets diffused, which is equivalent in mass to conduction in heat. So it gets diffused through a gradient of high humidity to low humidity here on top. So it gets diffused from the land pores or from the stomata in the leaves to the air on top. And then after that diffusion, it moves up again through convection in the atmosphere. So the latent heat flux is diffusion plus convection, and the sensible heat flux is conduction plus convection, right? Okay, so we talked about soil moisture limitations. What do I mean by that? And I mean that if you actually have soil moisture dropping below a certain threshold that we call critical soil moisture, then it starts affecting climate. It starts affecting the partitioning of latent and sensible heat flux. So suddenly you have little water in the soil, so low water lower than critical soil moisture. So there is more radiation being diverted to sensible heat flux to warm up, less to latent heat flux to evaporate water, because there is no water evaporate. Less water can potentially evaporate. So the sensible and latent heat flux are competing heat dissipation mechanisms, right? So you have the radiation, if one increases, the other one decreases, right? So when soil moisture starts going down, the sensible increases, the latent decreases. There is less evaporation because the soil moisture is not there. Okay. So we talked about land feedbacks, specifically about soil moisture feedbacks and vegetation feedbacks. We talked about the fact that vegetation may actually cool down temperatures, sometimes warm up temperatures. We talked about the fact that if you have little soil moisture, it's likely that it gets warmer because you have more sensible heat flux, and so on. Those, we will see them later in the last few lectures of this course. Actually. We talked about land cover geoengineering. We said, well, if vegetation affects climate, it affects temperature, it affects precipitation, then of course land cover and land cover changes affect climate, right? So you can plant a forest and you change climate. That, if you do it with the intention of changing climate, not to get wood or recreational properties, forest, right? If you do it with the intention of changing climate, that is called geoengineering or climate engineering. So you're engineering your climate. Okay, we'll see that also later. And the atmospheric underlayer. So the atmospheric underlayer, we're going to be discussing it today and especially next week. That's the thin layer of a few hundred to a couple of kilometers deep that goes from the land surface to the height. That is actually well mixed. It mixes through conductive convection because of the warming of the surface and the moistening of the surface, right? So when you have the radiation here that powers these sensible and latent heat fluxes, the atmosphere here is getting warmer and moister, and as a consequence, it's getting lighter. And as it gets lighter, it moves up through convection and starts mixing with a certain depth of the atmosphere, of the troposphere, the lower part of the atmosphere. That depth that is mixed, that is well mixed, is actually called the atmospheric underlayer. And we will go through that, especially in the next lecture. But it's where most of the meteorological events happen: rainfall, wind, temperature, heat waves, droughts, where we live, where ecosystems actually are exposed to the passing atmosphere. So that chunk of the atmosphere is the one that we hear the most about. This is the last few kilometers, as I said, of the troposphere, where we live. And that's why we are actually investing the energy of learning that, but also because it's the layer that is affected by the land surface properties. It's not just the layer that is in direct contact the plants and ecosystems and we are in direct contact with, but it's also one that we are influencing directly by changing land cover, for instance. Okay. So this is a lecture course content of the lectures that we're going to have in the course, and today is the second one. As you can see, we're starting the atmosphere actually because the other day was a bit of an introduction. So we'll have three. Actually, this is not the right. Let me see. I think I'm actually showing you the wrong course content layout because we had a change in here. I should have updated this. I'll update it later in the one that is in Zoom because we have actually a switch in the practicals. They happen now between lecture 4 and 5, 7 and 8 instead of after 8 and after 5. So I'll update that. The order of the lectures is fine. So we're going first for the atmosphere and then we're going to the land surface and then the feedback. So I'll update that in Zoom. Two things to mention before we go into the theory of today. One is that it would be great if you guys can send me the groups and the papers that you picked by next Monday, if possible. So you have to coordinate a little for that. The second thing is that the questions that you have during the lectures, don't hesitate to just raise your hands and interrupt me because it's probably better. I think that most of you are sometimes shy when it comes to actually ask things that you didn't understand. And if the ones that are not shy actually only come after the lecture to ask, all of you that didn't dare to ask don't get to know the answer. So I'm taking for granted, and you should take for granted that if you have a question, you're probably not the only one that has it. So it'll be good to kind of like clarify concepts as we progress. The only disadvantage of that is that we may delay a little the lecture. So if you have things right after the lecture, it will be good that that we don't take too long. But one thing that I saw that tends to be good is that we don't have any lecture time after hours. So if you take a few more minutes, in theory at least, it shouldn't be a big deal, unless of course you have other commitments. So first thing, water properties. I think that this is something that you see in secondary school. Some of them are very important for us, some of them are less important. So I'm just going to focus on the ones that are really important. Less important ones, well, you know, the water is meant to be inorganic, it's meant to be tasteless, at least if it's only water. It's meant to be colorless, odorless, neutral, insolent. All those are properties that reflect all the chemical properties and chemical composition of water. There are a few aspects that are particularly critical and that you can understand better when you think about the molecule of water and how it is organized. One of them is the high polarity. The high polarity of water implies that it's very good at solving or dissolving salts. So if you have, for instance, a medium in which you have salt, it breaks in ions and then it's associated to the atoms of water, and it's very easy to actually dissolve and transport that. So that is in nature important for contaminant transports, for instance, rivers and so on, or in our aquifers. And it's also quite crucial for plants to withdraw their nutrients right from the soil. So essentially, that's a function of water that is quite important for the hydrological cycle in relationship to plants that essentially provides a medium for nutrients to be transported. Okay? Now, I'm going to jump to the third because the second is probably most important. Water also has a very low solid density because the maximum density of water is about 4 degrees, and that has an important implication for climate, which is that ice floats, which of course for the ocean dynamics and many processes in our planet is quite important. So you have a very low solid density. You have the highest density occurring at 4 degrees when the water is still in liquid state. And then when you start cooling it, the density starts becoming lower, which implies that the ice at -0 is lighter than the water that is at 4 degrees, for instance, or between 0 and 4. That's not the only reason why ice floats in the sea. In the sea also, of course, the salt is making the liquid water heavier, right? So it's a little against that. And that's also one reason why the ice that doesn't contain that much salt is actually floating. But that's an important property of water for the climate system. Then you also have another property, the property number 4, that is something that you know from Kathy's lectures and so on, that is that the molecules of water, they are very tightly connected through hydrogen bonds, and that implies that there is a high cohesion. So it's hard to break a column of water, right? So water tends to stick together. And in addition to that, it also has a high adhesion, which means that it tends to stick to anything else as well, as long as it has a charge, especially, right? So why is this important? It's very important, for instance, for the hydraulic transport of water, not just in plants, but also in soils, because you'll see that the water molecules that tend to stay together and they tend to stick to the walls of the pores and the capillary tubes and so on. Okay, so that of course is quite crucial for instance, the cohesion, tension, adhesion theory. So how plants are actually withdrawing water and bringing it up to the leaves. So that high cohesion and adhesion has to do with again the molecular properties of water. And the last and most important thing that I wanted to mention is got to do with the high specific heat and high latent heat of water. So what does that mean? It means that water takes a lot of energy to vaporize. It means that water takes a lot of energy to increase its temperature, right? So much more than most of the materials we have on Earth, right? So that is important for one thing in particular, is that water tends to regulate or dampen, buffer, attenuate big climate changes. So if there is a heat wave coming and you have water in the ground, the water will take energy to vaporize and a lot of energy to warm up. So a lot of that energy from the heat wave is actually sent into the sun, into the processes of vaporizing and changing the temperature of water. So water is kind of like a buffer of the atmosphere effects on Earth in that sense. And that is conceived by these high specific heat and high latent heat of water, right? The latent heat of water, lambda, and this is actually just coming to physics in a way that you may actually get some concepts clear for later that you may actually see in formulas. So this is actually important for you to understand. So the latent heat of vaporization or the latent heat of fusion or solidification is this lambda. And that lambda you can see many times in my slide. You saw it the other day already in the energy balance. That lambda, if you think of the lambda for vaporization, for instance, is the amount of energy that 1 gram or 1 kilogram, it depends on what unit you use, of water takes to evaporate. All right, so it's per mass. This in here. And you can look at the units, and probably the units are better definition sometimes than the words that you have afterwards. So it's in joules per kilogram. So how many joules you need to vaporize 1 kilogram? That we call it lambda, or latent heat of mostly vaporization. Is what happens in nature, as I mentioned before. But if you go to a region that has snow, then it will be quite important to think of the latent heat of fusion. So how much energy it takes to melt 1 kilogram of snow or ice, right? And one thing to bear in mind is that fusion and solidification are symmetric processes. So the energy that is taken to melt is the same energy that is actually released later when the liquid turns into ice again. All right? So the latent heat of fusion and solidification is the same, it just works both ways, it's symmetric. And the same for vaporization, as we mentioned the other day. The amount of energy used to vaporize water is the same that is released later up in the atmosphere, on top of the atmospheric vapor layer, when that water vapor condenses. All right, so the latent heat of vaporization and the latent heat of condensation are the same. Right here. So we mentioned the other day, you have certain energy here, vaporize the water. That water vapor is energy in latent state. That's why we call it latent heat flux. So that water vapor moves up in the atmosphere, and is then, when it cools down and condenses, that it releases that energy. So there's a latent heat flux. Okay. So if you look at the numbers, and the only ones that I care about are the ones that I read here, you can see actually that the latent heat of vaporization is higher than the latent heat of fusion, and trust me on this, very high compared to other materials on Earth. And it's also higher than the specific heat, and I'll tell you what the specific heat is in a second. And as I said, the specific heat for water is still very high. So now this specific heat is the amount of energy that it takes to warm up by 1 degree. So the same way that the latent heat, the lambda, the latent heat of vaporization is related to the evaporation, and the lambda E, the latent heat flux. The specific heat is related to the sensible heat, to the warming, right? I mean, it goes, maybe I can repeat this because I saw some looks like, I'm not sure if this is clear. It goes without saying that this latent heat, this lambda, when you multiply it times the kilograms of water evaporated in evaporation, then you get the latent heat flux, kilograms or liters. You can put the evaporation units you want. Of course, units are, you just have to get the units right. But you can choose. I mean, it's better to use the international system. So lambda E is latent heat flux. Lambda is latent heat, or latent heat of vaporization. E is evaporation. So latent heat of vaporization times evaporation. In other words, the energy that takes to evaporate times how much it has been evaporated is the total energy that is involved in that evaporation, which is the latent heat flux. Lambda E. And if you want to think of it differently, if E is evaporation in water volume units, if you multiply it times lambda, you get the latent heat flux that is evaporation in energy units. That's it. So you can think of lambda as a way to convert your evaporation into energy, because it's the energy that it takes to evaporate 1 kilogram of water. The specific heat is the energy that it takes to warm up 1 kilogram of water. Warm up by how much? By 1 degree. Okay, that's the definition. So it takes much less energy, about 1,000 times less, because you see 6 in here, this 3 in here. It takes about 1,000 times less energy to warm up 1 kilogram of water by 1 degree than to evaporate that 1 kilogram of water. All right, that's what you can actually be used from this. Still, that specific heat is very high compared to other materials, as you say. Proof is that if you have the sun shining and you put a puddle of water and you have black soil next to it, I can assure you that the black soil is going to get super warm very quickly with the sun, and the puddle of water is going to change very little the temperature. That's because the specific heat of water is very high, still much lower than its latent heat, as I mentioned. Now, we call it specific heat because it causes a heat that is actually, well, specific is used in physics usually to refer to mass. So when you say per kilogram, that is usually what it means specific, right? Now, we can also actually express that in volume per cubic meter, and then we call it heat capacity, right? You see the units here? This is just joules. So energy that takes, work in this case, energy that takes to warm up by 1 degree, 1 kilogram. Well, if you put this in cubic meters, you have the energy that takes to warm up 1 cubic meter per 1 degree. Degree Kelvin or degree Celsius is the same, right? Okay. And how do you convert one from the other to the other? Well, with the density. One is in per kilogram, the other one is in volume, so you just have the density here. And actually, if you want to multiply these units like this, it's the kilograms goes, and then you have joules per Kelvin per cubic meter. So the specific heat times density is the heat capacity. So specific heat, how much it takes to warm up by 1 degree. 1 kilogram heat capacity, how much it takes to warm up by 1 degree, 1 cubic meter. Nothing else. Okay? And that's usually denoted by a capital C, and this is usually denoted by a lowercase c. And the one that you're going to see the most in this course is the heat capacity at constant pressure. Is this with a low subscript P? That means that the pressure is constant, because in fact, depending on the pressure, you can have a different, or you can cause changes as a function of pressure in the heat capacity. So that's why you just look at it at constant pressures. Right? So yes.
The latent heat flux is lambda.
Yes. So the latent heat of vaporization is just lambda. That's what takes to evaporate. For instance, we can also think of it in volume. It doesn't matter too much. Let's say you have a unit that is a glass of water. So you can think of the amount of energy that takes to evaporate that. If you multiply times the number of volumes of glasses of water that have evaporated, which will be E, the evaporation, then you have the total energy. Yeah. The unit of E is kilogram. If you want to express it in joules later, the unit of E usually is expressed in watts per square meter if it's in energy, or in millimeters if it is in volume, like precipitation, because it's millimeter per square meter. But in reality, it's the volume per time. So when you express, like the most common unit that you'll see of evaporation will be millimeters per day. That's a typical unit. The same as for precipitation. When you hear, today we had 100 millimeters of precipitation, which is like a superstorm. What that means is a depth of 100 millimeters. That's not 100 millimeters at all, but it's more like this, right? 100 millimeters per square meter of soil in a day. So in reality, it's a volume, because that per square meter of soil will be a volume. 1 millimeter is 1 liter, so you can calculate 100 liters. 100 liters in a process of a day. So a flux is measured in volume per time. That's the typical unit of a flux, like evaporation or precipitation, volume per time. When you want to express it in volume, so kind of like from a hydrologic centric perspective, but you can also express the evaporation in energy. So instead of giving the volume that is evaporated, you can give the energy spent in evaporating the volume. And if you do that, you have to multiply that volume times the latent heat of vaporization, this in here, and you have to get the units squared. So you need to know, in fact, the density of water, which in case of liquid water is 1, usually. I mean, you can assume it is 1. So you can do that conversion. Yeah. Okay. Yes. So now a bit more into chemistry, but not real chemistry. We're not going to touch much on chemistry in this course. So one thing to bear in mind is that in this course, of course, water is quite important, but the atmosphere is also an important component of this course. We can also apply the same things to the atmosphere. We can think of the specific heat of air, how much it takes to warm up the air and so on. Okay. Now, what is the atmosphere? What is the air? And I know that you know this, but it's good to review it a bit. The air is a mixture of gases. Is what it is. It's a mixture of different gases. Mostly nitrogen, almost 80% is nitrogen, and almost 20% is oxygen. And the rest is just very small. Have some 400 parts per million of CO2. You have water vapor, that can be more, that can be like 3% when it's moist, but you can also have completely dry air. And in fact, the composition of the air, except for the water component, is pretty stable. The water component can be variable from 0 to 5 or 10% of the air. Because the water spends very little time in the atmosphere. It has a very low residence time. It's much more dynamic. You have evaporation, and usually it takes about 10 days on average for that water to fall back in the form of rainfall. So that dynamic component of the composition of the air is really coming from the water. The nitrogen, the oxygen, they have a much longer residence time, so those compositions don't change. It's really, but the only thing that really are, of course, you can have pollutants at a certain time, contaminants into the atmosphere. But usually when you look at the atmospheric composition in more pristine environments, what changes the water content. You can have a lot of water content, less water content. That humidity is really very variable. And that has to do, as I say, with the residence time of water in the atmosphere. It's just simple physics, right? So if you have a lot of water coming and a lot of water leaving through precipitation and evaporation, then you will have actually a very quick emptying of that reservoir of water in the air. So this guy, John Dalton, what he discovered actually is that the air of any other mixture of different gases, the pressure that it has is in fact equal to the summation of the individual gases pressure, or how we call it partial pressures of different gases. So this is actually probably clear if you look at this. So if you were to have two gases, in this case it's actually hydrogen and helium, the pressure of each of them, or when they are in a mixture, we call it partial pressure, is actually this in here. Why is this in here? Well, the pressure, if you remember, actually is a force per surface, all right? Force per area is what pressure is. You have the units in here, by the way, if you want. So you can express pressure. Usually we use pascals, which essentially means, if you want to think of it in units of actually international system units of mass, time, and distance, is kilograms per meter per second. And I'll tell you why it is actually. But you can also think of pascals as joules per cubic meter. So it's just the volume, and joules is work, right? So it's work per volume, or force per area, as I just mentioned. Force per area is newtons per square meter, right? So pressure is a force per area or a work per volume, which is the same. And if you know that force, these newtons actually are equal to mass times acceleration, right? You know that force is mass times acceleration, then you can actually get this kilograms per meter per second square. That comes from that. Calculate it in 10 seconds if you want. And also take my word. So this is pressure is really, you can think of it as a force per surface, right? So one way to measure pressure, you have a gas, is to actually put an equivalent force on top until it's in equilibrium, what we call hydrostatic equilibrium. Right? So if you put, in this case, you put a couple of weights in here, the weight, so the mass times the acceleration of gravity here will be equal to the pressure that you want to work out. So that's how you measure the pressure, right? So you put two weights in here, and you know that divided by the surface of that disk will be the pressure of the gas. Well, that's just a long explanation of something that you don't necessarily need to know, but if you think about it, you probably work it out yourselves without problem. But the thing that I want to mention is that if you have two different gases and you mix both of them, the pressure that you get is the summation of the individual pressures. And this was actually this guy that we put up. Now, if you think of the air, of the atmosphere, what that means is that the pressure of the air equals the pressure of nitrogen plus the pressure of oxygen and so on. And of course, the pressure of water in that mixture, which is the atmosphere. Now, that partial pressure of water in the air mixture is called the vapor pressure. And that's going to come in pretty much every lecture throughout this course. So it's a way to measure humidity in pressure, the partial pressure of water in mixture of air. That's what it is. It's water vapor in the air mixture. So we know the atmosphere, the air is a mixture of gases. One of those gases is water. The partial pressure of water is called the water pressure, water vapor pressure, all right? So it's just a way of measuring humidity in units of pressure, nothing else. By the way, I mentioned that pascals is equal to all this, and is the unit that we usually use because in international system units. But you also hear sometimes atmospheres as a unit or bars. Bars is also common. So not going to give you the translation now. You can look it up if you want. It's not important for this course, right? But keep in mind that the water vapor pressure is the pressure of water within the mixture of air. Okay. So let's think about dry air and its composition, because I want to get to one conclusion with this slide, and I hope it's clear. If you look at the composition of air, and these are just percentages of each of the component gases of the air sample, you can see that almost 80% is nitrogen gas, right? And as I mentioned before, about 20% is oxygen, and then you have a few other components. If you have dry air, implying that the water vapor pressure equals 0, so there is no water vapor, its composition or its percentage within the entire air is actually 0%. That's what this means. You can calculate how much that weighs, each of those components weighs in the mixture of air. So you can put it actually in kilograms per mole of air, if you wish. And you can do that by using the molar mass. I'm not going to go through this because it's like high school chemistry, but if you multiply these two things, you can see it works. So you have the percentage of each of the gases multiplied times its weight of each of those gases, and then you get how much they weigh compared to 1 kilogram of air, if you wish, or 1 mole of air. So you're calculating how much each of the gases add to the weight or to the mass of the air, all right? And if you do it, one thing you get is that the typical mass of air is about 28.87 grams per mole, all right? Now, what I actually want to get is to this. If you add moisture to that mixture, so if you add water, even if it sounds counterintuitive, because that water has a very low molar mass, so it's very light, the molecules of water are light. Think about it that way. When you add, for instance, a 3% of water, since the percentage of the others is actually decreasing, you end up with a lighter air. So moisture air is not heavier, it's actually lighter. So when you have air with moisture, when you have air with water vapor, the air becomes lighter, okay? And why do we care about this? Because we mentioned before, you have your radiation and you warm up the air and then it becomes lighter and it moves up. But if you use your radiation to evaporate water and you moisten the air with that, then it also becomes lighter and tends to move up, right? So both latent and sensible heat flux are making the air lighter and inducing convection in the atmosphere, right? Okay. Any questions? Now, that is the water vapor pressure. Now you can think of a certain pressure that the air can take before it saturates. If you add a lot of vapor to the atmosphere, at some point it saturates and it starts forming droplets. So liquid water, right? You can saturate the air. That point of saturation, the vapor pressure of saturation is this. It's called E star. So the normal water vapor pressure, the vapor pressure that you have, the actual one, is called E, as you saw before. The saturation one is called E star, is the amount of water that you can have in a certain atmosphere before it saturates. So the point of saturation, if you wish, measured in units of pressure, in pascals. So that's called the saturation water vapor pressure. Saturation vapor pressure, that's very important as well. And as we mentioned the other day in the lecture, when you have air that is warmer, the saturation water vapor pressure is higher. So warm air can hold more water vapor. cold air can hold less water vapor, right? And it's like exponential. The relationship is exponential. Is this exponential here? And that is called the Clausius-Clapeyron law, all right? And it's crucial for any climate model. It's crucial to understand climate change, and it's very important for this course. So what implies, for instance, is that if we move into a future that is warmer, the air will be able to hold more water vapor before it rains, which may mean that sometimes you have less rain, but it may also mean that you have more water in the atmosphere and more rain, right? We can go through that later if you want. This equation here, of course, you don't have to know it, it's empirical. It's just this guy, Clausius actually, he's not trying to fit this curve and coming with these coefficients, but this is a description of this function, which is merely empirical. So just don't need to know it, but you need to know that the shape is exponential, of course, because it has important implications. It means that, for instance, if you, as I mentioned the other day, if you're in the tropics at 20 degrees and you raise the temperature to 30 degrees, so by 10 degrees, you can hold a lot more water vapor in the atmosphere than if you're at 0 degrees and then you raise it to 10 degrees. So this is very small, but yeah, this is huge. All right. Now let's see some concepts. One of them is this VPD that you already see there. Okay. This VPD, vapor pressure deficit, is just the difference between the saturation vapor pressure and the actual. Nothing else. Super important concept as well. Vapor pressure deficit. So kind of like a measure of the aridity of the atmosphere, the dryness of the atmosphere, right? So how far you are from saturation in terms of pressure, in units of pressure, right? VPD. Usually in English it's called VPD, like that. You just read the acronym. Now, we said that we are expressing the vapor content of the humidity in units of pressure, but you can also express it in kilograms per volume or kilogram per mass of air. So kilogram per kilogram, if you want it. So if we express the amount of water vapor in kilograms of water vapor over the kilograms of air, then we call that specific humidity, Q. That's in kilogram per kilogram of water per kilogram of air, right? So it's the mass of water vapor per mass of air, specific humidity, right? That's Q, and it's related to E, to the vapor pressure, like this. Now this comes from molar masses, you don't need to know it, it's just a constant. The only reason I put this equation here is for you to realize that this Q and E for a certain air pressure, E is air pressure, so the pressure of an entire mix, not water. So for a certain air pressure, E and Q are related linearly, all right? So you can convert from one to the other. You just need to know the atmospheric pressure. You know the atmospheric pressure, you can put the humidity in units of pressure, so water vapor pressure, or you can put the humidity in units of specific humidity, so kilograms per kilogram, right? So they are very related to each other. What you usually get, actually, if you buy, for instance, a dehumidifier for your house, and you say, well, I want it to be humidity 80%, that's quite large, 40%. That 40% is relative humidity, all right? So relative humidity is this, it's just the actual humidity divided by the saturation humidity times 100. You can think of it in pressures. So water vapor pressure divided by the saturation water vapor pressure times 100 as a percentage of saturation. Or you can actually, because you can see it's the same, this goes, if you want to present this in mass specific. Mass is specific, right? We said the most specific mass, specific humidity, kilograms. So you can also express it in specific humidity divided by the specific humidity as saturation. We call it Q star, which is analogous to E star, right? So it's how many kilograms the air can hold before it saturates, or saturation, right? So that's the relative humidity. Okay. And it's very sensitive to air temperature, as you can see. You increase your air temperature and you have the same amount of moisture in the air, your relative humidity goes down because you're increasing this, the saturation point. So if you increase the air temperature, this saturation point goes up, right? You can see it here. So if you think of, for instance, warming up a certain air with a certain content of water, if you actually warm up that air, you're getting it relatively dry. So the relative humidity goes down. Does it make sense? So the relative humidity goes down when you separate more from saturation. So if you warm up the air, your saturation point is higher. You have the same amount of moisture, you're getting it relatively dry. Relative humidity is going down. Your specific humidity is the same kilograms per kilogram, but your E star or your Q star are actually okay. And one concept that is also important, because you'll see it comes later, for instance, in the Pema-Motif equation that we said here, that was the most important equation of these bars, is this delta here. That delta is the slope of that relationship, right? We don't even have a name for it, just call it delta. So it's the slope of the Clausius-Clapeyron relationship. And you can see it's high when the temperature is high, and it's low when the temperature is low. You can see the E star, this curve, the saturation point depends only on temperature. It does not depend on humidity, it depends only on temperature. You have a temperature, you can tell exactly what it is, right? So it's just a function of temperature, saturation point. Okay? And the slope of this curve, of course, is also a function of temperature. You have high temperature, the delta will be high. And it's just the differential of the two, right? It's just a Jacobian differential of temperature divided by differential of humidity. This is the slope. Okay? So those are important concepts. As you can imagine, if you move air here, you have liquid water condenses, right? And if you move air in this direction, it gets vapor, right? So this is separating vapor from gas. It's the saturation curve. So essentially, you can, if you were to be here in A, let's say that is your air, it has 25 degrees temperature and like 1800 pascals of pressure, of air, of pressure, not of atmospheric pressure, but pressure of water, so water vapor pressure. That is in gas, but if you move it to this area here, the water condenses. Now, how do you condense it? You can either go and add more moisture, so you move in the vertical here, or you can reduce the temperature and it condenses. So essentially, if you have a certain air and you want to condense the moisture in it, you can either, of course, add more moisture until you surpass the saturation, or you can cool it down until it saturates, okay? Like it happens in the atmosphere, you move the air that is moistened here by the latent heat flux up in the atmosphere, it cools down and forms clouds. And we will go through that later, actually. Okay. Still, we have a few more concepts here, unfortunately. Dew point temperature, that's actually a concept that you will see in the future if you do anything related to micrometeorology or meteorology in your life. The dew point temperature is really just the temperature to which you have to cool down your air until it saturates. So it's this. You have your air here, you cool it down. That point, that temperature is your dew point temperature. Pretty easy, right? So you just cool down your air until it saturates with the same humidity that it has. That point at which it saturates, your dew point temperature, right? That's why we call it dew. Dew in the morning when you have dew forming on the leaves of the vegetation, for instance, is because the air has been cooled down because it didn't have the radiation from the sun and it was emitting no light during nighttime. So you have the cooling down at night of the air, and then it forms dew, which is condensation on top of the leaves or whatever. All right. Now, dry bulb temperature is just temperature, actual temperature. This is a confusing way to call it. Now, the only reason why we call it dry bulb temperature sometimes is that we have an equivalent that is the wet bulb temperature, an analog of wet bulb temperature, and I'll tell you exactly what we do with it. So you can have humidity measured essentially two ways. You can measure it with what we call an hygrometer. This that uses the dew point temperature. What does it do? Essentially, it cools down the air until it saturates. When it saturates, then it says, okay, I'm here, so that's my moisture content, because you're moving in a horizontal, so the hygrometer cools down the air, and then when it saturates, okay, this is the humidity that I have. You don't know it until you saturate it, right? So essentially, you're here, but you don't know where you are. You may measure your normal temperature, but you don't know how much moisture you have. So you start cooling down, and when it saturates, it's like, okay, so this is the humidity that my air has. So that's how the hygrometer works. Cools down the air until saturation appears, and that tells you how much moisture was there, right? All right, so that's a way to measure humidity in the air. Another way is to use what we call a psychrometer, which is a couple of wet bulb and dry bulb thermometers. That's why I'm actually talking about this now. So psychrometer, the way it works is it measures both the temperature that actually has here, the dry bulb temperature, as we call it, with a normal temperature thermometer, normal. And then it has another thermometer that is covered usually in a wet cloth or something that is moistening the thermometer that we call the wet bulb thermometer that measures what we call wet bulb temperature, right? And it compares it with actually this equation that you don't need to know, all right? But there is a reason it's here, and I'll show you now why. But, so an hygrometer just pulls down the temperature and measures the humidity at saturation. A psychrometer has two thermometers, one that is a normal thermometer and one that is covered in a wet cloth. Why do we do that? Because the one that is covered in a wet cloth is measuring this that is called the wet bulb temperature. The other one is just measuring the normal temperature, which is this dry bulb temperature. The wet bulb temperature will be lower and the humidity will be high. Why? Because your wet cloth, what it's doing essentially is cooling down the thermometer and the air on top by evaporating water, right? So essentially it's taking the air temperature, specific heat if you want, to vaporize the water that is in the cloth. So at the same time, you're getting more humidity in the air coming from the cloth and a lower temperature because the air is passing the energy to evaporate the water from the cloth. That's why this moves in the diagonal. So it moves to higher humidity and lower temperature at the same time. And that wet bulb temperature, when you measure it, and you also measure your dry bulb temperature, you can apply this equation to get the humidity of the air. So that's a very common way of doing it with this thermocouple of wet bulb and dry bulb temperature. And the part that I care about is this gamma here, which is called the psychrometric constant. Not because I'm particularly fascinated by it, but because it comes later in the Helmholtz equation. And you say, what is the gamma? Well, that's the psychrometric constant. It's just telling you how these two relate. The humidity of the air, the saturation humidity, and then the temperature, dry and wet bulb. So those factors essentially is telling you about the diagonal shape. It's like this, like this, like this, like this. That is the psychrometric constant. So that's where it comes from, because you'll see later in the equation of Pema-Montes, and you'll hear out that it's the closest Clavier one explains it. All right, so it's just a relationship between the humidity and temperature simplified into one parameter that in fact is not a constant. We call it psychrometric constant, but it's a function of pressure. But well, let's keep that out of your brain. But concepts that you need to know here, of course, relative humidity, specific humidity, vapor pressure deficit. You don't need to worry too much about the dry bulb and wet bulb temperature, but you need to know where the psychrometric constant comes from, because it will come up later in the course. And the dew point temperature is an important concept because it'll come many times in the future. Anything related to atmospheric science. Dew point temperature, super easy. Yeah.
What's the function of the soap cloth exactly?
So the soap cloth, what it does is essentially providing a source of moisture to the air. At the same time, that is actually extracting energy from it, so cooling it down. So essentially, what it tries to do is moving the air away from this point within the spectrum of humidity and temperature to see where it lies into this function, so that you can actually use that behavior to work out your actual humidity that you have before you put the wet gas.
So the water evaporates and it goes into the air.
Yeah. So yeah. So it's the thermal couple is measuring, one is just measuring normal temperature, and the other one that is actually wet is measuring the temperature of the air right on top that is being moistened by the evaporation that happens by using the energy of the passing air and therefore cooling it down. It's kind of like a thermodynamic equilibrium in which you have essentially a surface of water and the air right on top is losing temperature to vaporize water until it reaches some form of equilibrium, that is saturation.
And that's why the amount of moisture in the air is
Up to saturation, yes. That is the permanent equation. Still pretty ugly because we haven't seen any of the terms, but we will actually derive it later in the course. And one thing I wanted to point out is that we already know quite a lot of the variables and parameters are coming here from this lecture. We've seen the density. In this case, it's not the density of water, which is what I mentioned before, but the density of the air. This density here. We have the specific heat at constant pressure. When you multiply the density of the air, you have the heat capacity. We can call it also heat capacity. This density times specific heat. And that's a constant pressure, as I mentioned before. That's why it has a subscript here of P. That, as well as the density, is not the specific heat of water, as I mentioned before, but the specific heat of air. So how much energy the air takes to warm up by 1 degree. The property of the air. That goes in here. I'm not going to explain the formula now, but eventually things will come up together. This in here is the vapor pressure deficit. So vapor pressure at saturation minus the actual. So all this is the VPE. This in here is the slope of the saturated water vapor curve. So the Clausius-Clapeyron equation, the delta, which is a function of air temperature. We said, like if you warm the air, it will be steeper, right? This is this exponential curve, is the slope of it, and the psychrometric constant that you have in here. Okay, so some terms already starting to come up. So we have a few pieces of the puzzle. We still miss a few others before we can actually derive the equation, but we'll go through them in the lectures that you see there. All right. And the derivation is on the lecture 6. I have a quiz now. Okay. So you've heard in the news for sure that wet regions are getting wetter, but you also have heard that dry regions are getting drier. So that is actually something that doesn't seem to equate too well with what I mentioned with the Clausius-Clapeyron. The Clausius-Clapeyron equation implies that if you have higher temperatures, you'll have more moisture in the atmosphere. Higher saturation points, you may have more evaporation, more moisture in the atmosphere, and therefore you may have more rain in the future. You may have actually more floods and so on. So it equates more with this wet gets wetter, but this dry gets drier is what I actually want to inquire you about. So why do we have that dry get drier? Now, one of the reasons can be because we have also some regional cooling, and it's there where we expect the drying. It can be because rain will preferentially occur over the oceans. It can be because land has to provide more moisture to reach condensation. It can be because the increase in aridity and droughts is completely unrelated to the Clapeyron equation, or because God likes it dry and hot. So, let you have a look at them. The question is again, how do we explain the fact that dry regions in the future may actually become dry with what we have heard today or in the previous lecture actually? So the answer number one is because there will be also regional cooling. Is that voted by anyone? No? Okay, good, clever. B, rain will preferentially occur in the oceans. I'll look at your mates like, that sounds kind of legit. Land needs to provide more moisture to reach condensation and yield rain and seems enhance that. The increase in aridity and drought is not related to the Clapeyron equation. God likes it dry. Some of you didn't raise your hands, so I presume you take it. All right, so yes, you got it right. So land needs to provide more moisture to reach condensation. That's the right answer. So what you usually have is kind of like this wet gets wetter. That is easily explained, right? So you have more energy coming to us because of the greenhouse effect, so more net radiation, more energy to evaporize water. And in addition to that, you have the air being warmer because you also have more sensible heat flux, that's global warming. So you have a combination of air being able to accommodate more water vapor because it's warmer, and a more powerful latent heat flux, more evaporation, so there will be more water vapor in the atmosphere. So far, so good. Now, if you're in a wet region, that may imply that then you form more clouds, you have rainfall, you may actually have kind of like what we call an acceleration of the hydrological cycle. So more rivers, more aquifer recharge, and at the same time, you still have more evaporation and more precipitation and so on. There's an intensification of the hydrological cycle. Why doesn't it work like that? In dry regions, you have a limited amount of moisture in the soil. You are below critical soil moisture, right? So what happens is that most of the extra radiation and temperature doesn't go to evaporate water because the amount of evaporation is still not going to change too much if you change the temperature of the air, because essentially everything that's there eventually evaporates, it's just dry, right? So not much more evaporation, and at the same time you combine it with a warmer atmosphere. A warmer atmosphere means that you can hold more water vapor, of course, but you also have a higher point of saturation. So to saturate a warmer air, it takes more moisture. If you don't have more evaporation and the high saturation of the atmosphere is there, then of course you're not going to form clouds, you're not going to yield rainfall. That is the reason why wet regions tend to get wetter and dry regions tend to get drier. And in addition, there is a very important land feedback to that, is that if you have a region that is getting wetter, tends to evaporate more, tends to rain more. If you have a region that gets drier, because suddenly you have less rainfall, as we were talking about, then you get even less moisture and even less rainfall because you have less evaporation and less moisture and so on. So you have that feedback in which as you lower the soil moisture, you get less evaporation, and therefore even harder than before to saturate the air, and that continues as a positive feedback because it just kind of self-accelerates, right? Okay, good. I think I'm just going to continue for like 5 minutes because otherwise I think we're going to have a second half that's going to be a little unbearable. So the structure of the atmosphere, something that you have already seen before in school. You have different layers. The one we care about is the troposphere. That's about 10, 12 kilometers, the height of which planes fly. That's usually the tropopause, where you have the break between the troposphere and the atmosphere. Okay? That is the troposphere. That's what we heard next. As you can see, the layering of the atmosphere, and you'll see this later in a course by Hans Verbeek on meteorology next year, is set by temperature gradients. That's how we rate the atmosphere. So it's a layer in which the temperature goes down then a layer in which the temperature goes up, and so on. That's the actual temperature, not the potential temperature, and that is something that we'll see later. Because what we care about really for climate is the potential temperature, and that you can hold it in the back of your brain because that is going to come up later. Okay, but just keep in mind that that layer of actual temperature sets the different parts of the atmosphere, and the one that is next to the ground is the troposphere. And just the very few 100 meters of the troposphere are the ones that really matter for the influence of land and for the development of meteorological events, and is what we call the atmospheric boundary layer. And that's the black box that I wrote in there. Okay, that atmospheric boundary layer is the one that we care about in sport. So we care about from the top of the atmospheric boundary layer until the bottom of the roots. That is really where we have our exchanges of heat, moisture, carbon between atmosphere and land. That's the domain of our course, from the bottom of the roots to the top of the atmospheric boundary layer. And it's a vertical transport force. Okay. Point scale and consistent scale. Now, one thing that happens in the atmosphere is because of gravity, you have most of the atmosphere next to the ground. Most of the air gas components are next to the ground. So if you think of in terms of molecules of gas, they are all squeezed next to the ground because they are attracted by the gravity force, right? So essentially, you have a much higher pressure next to the ground than you have up here. Now that when you climb the Everest, some of you have done it, and the pressure of oxygen actually goes down quite rapidly, right? And that's essentially this. You have a much lower air pressure and pressure of all the gases that conform that air mixture as you move up, right? Okay, so the air pressure declines exponentially with height, as you can see here, and so does the density, because the density and the pressure are very related to each other. Okay, so the density of the air is also declining exponentially with height. All right. So keep that in mind because it's important. Now, you've seen this before, probably. I'm quite sure. Maybe you don't recall. Now, why is that all the air doesn't get squeezed down to the surface? Because of gravity. There must be something that is also pushing it upwards, right? So there must be a balance. If you think of the atmosphere at any given time, in which we have no important vertical motion. So let's not think about convection with the atmospheric boundary layer and so on, but just think about the air as it is in any single screen capture shot. So you don't have a strong vertical motion that have air sinking super rapidly and moving up. If that is the case, it's because the air is in some form of equilibrium between the weight, so what is actually pulling it to the center of the earth, and what is pulling it up. And what is pulling it up? Well, this, right? You have a pressure gradient. The air wants to go to lower pressures, like any other fluid, right? So fluid, gas, and liquid, the atmosphere is a fluid. So if you have more pressure on the bottom and less pressure on the top, then it's going to tend to move up. That is applicable to the air mix, but it's also applicable to any component. If you have more partial pressure of oxygen below than above, then the oxygen will tend to move up. And the reason why you don't see any vertical movement is because there is a balancing out of the weight of the earth and the pressure moving it up. So you have those two forces being equal. That we call it hydrostatic equilibrium, right? Hydrostatic equilibrium. And is this in here? Here we explain this hydrostatic law. You have the vertical changes in pressure that have to be equal to the weight of the air parcel. That applies to anything in reality that is a fluid. If you have the ocean and you have a layer of ocean or a parcel of ocean that you look at, and it's not moving vertically, it's because the weight that it has is equal to the pressure force that is moving, pulling it upward. Okay. All right. So before we take a break, I'm just going to mention one thing about this. Is that in the atmospheric boundary layer, we don't have hydrostatic equilibrium. We have vertical mixing, as we were talking about, right? So that is very important. Now, why do we have a vertical mixing? For two reasons. From the bottom, so from the surface, we are wetting and warming the air, and by making it lighter, well, you can see what happens when you make it lighter, right? Make this lighter so the density becomes lower. Then, of course, the air will move up because this is suddenly bigger than this. All right. So that's one way to break the hydrostatic equilibrium and induce vertical movement by warming it and by wetting it, because we're making it lighter. Another way is through roughness of the surface, obstacles, generating eddies, breaking this laminar flow and generating turbulence. Those are the two things that happen in nature. When we look at the atmospheric boundary layer, we saw, remember that video that we had the other day in which had like fire coming from land surface and it was mixing all together. That atmospheric boundary layer, that's a look at how it's actually well mixed, constantly convection, you have turbulence as well. That is generated by those two mechanisms, the moistening and warming and the friction. One we call it buoyancy, and the other one we call it mechanical. So mechanical friction, because it's just obstacles generating the breaks of the laminar flow, and that pushes up through changes in momentum. And the other one is just, it's called buoyancy, like buoys in the sea, when you have a buoy that is floating in the sea. We call it buoyancy when you have something, well, the buoyancy can be positive buoyancy if you have something that tends to move up because it's lighter than what it has on top, or it can be negative buoyancy if it tends to sink because it's actually heavier than what it has on the bottom. So those changes in buoyancy are changes in weight of a certain part of the fluid that makes it actually either sink or move up. So that's the way actually in which we break this hydrostatic equilibrium in the atmospheric boundary layer, by warming it and moistening it, because we make it lighter and that induces a positive buoyancy, or by friction and roughness of the surface that breaks the paths of the wind that makes it lift up. The former, the buoyancy changes are most important. Okay. If we go back to like basic thermodynamics, these two guys they have in here have been some of the fathers of thermodynamics in what comes as, at least to Earth atmospheric thermodynamics. So the first one on the right hand side, actually, because the oldest, is Robert Boyle. So what he realized, though, is nothing groundbreaking to you and it's fairly intuitive, is that if you have a certain amount, like think of air as a parcel of air from now to the end of the lecture. So it could be actually a parcel that has got boundaries or not, it doesn't matter too much. But think about kind of like a balloon of air. So if that air has constant temperature, when you change the pressure, you increase it, for instance, the volume decreases. Nothing you don't have intuition about already. If you decrease the pressure, it expands, so the volume increases. So that was first postulated by this guy in the 17th century. And then actually more than a century later, this fellow here, Jacques, realized that actually when you keep the pressure constant, there is also a relationship between the volume and the temperature. And that is maybe slightly less intuitive, but essentially what he says is that the volume is directly proportional to the temperature, meaning that if you have a constant pressure and you increase the volume, the temperature increases. Okay? So a few years later, they put together these two laws, and they came up with what we now call the state law of ideal gases, which if you don't remember from high school, you have to definitely put some effort on memorizing, because it's a very important law. It's imprinted in every single climate model or numerical weather prediction model, meteorological model, atmospheric model. So it's a very important law. I wrote it here as well. So PV equals nRT, even if you don't know what it means. That's important to memorize. One of the few things that even I will actually ask you to learn by heart, because it will help you later understand some processes in the atmosphere. E stands for pressure, V is the volume, M is the number of moles, universal gas constant R, and T. What you care the most about in there is PV and T. Okay, so the pressure and the volume and the temperature. Pressure and volume will be inversely related, because if you increase one, the other one has to decrease if you have constant pressure, temperature, right? And then temperature relates directly with the other two, in the sense of if you keep this one constant, increase temperature, pressure has to increase. And if you keep pressure constant, which is what we call in meteorology isobaric process, constant pressure, if you increase the temperature, the volume increases, which is what Jacques Chard pointed out already back in the 19th century. So, important law, okay? It applies to the entire atmospheric mixture of gases, but it also applies to all the constituents. I don't need you to learn this, and that's why I shaded it. But just for you to bear in mind that you can apply to each of the gases within the mixture, not just the total mixture of air. So if you look at the, for instance, the water vapor pressure instead of the pressure, and the volume of water, and so on, it also applies. Okay, good. Might be sometimes that it's easier. It might be easier sometimes to actually think of this in terms of densities. If you want, you can actually bring the volume here, and then n divided by v is actually kind of like the molar density. Okay, so if you want to think of air density, you have to be aware of the fact that the volume is inversely proportional to density, or volume less density for the same mass. Okay. Sometimes density is a bit more intuitive than volume when we think of gases, because they don't have a volume. They're not confined to a container, right? At least in nature, I mean, not in a lab. Good. Now, we've seen already the hydrostatic law, and we have seen the law of ideal gases. Very important ones, okay? Now we're going to see a third one that is quite intuitive as well, but it's slightly more complicated, which is the first law of thermodynamics. The first law of thermodynamics is just the law of conservation of energy applied to a thermodynamic system, so the atmosphere, for instance, right? So what it's telling you is that the energy cannot be created or destroyed, it has to be transformed into another form of energy. Okay? First law of thermodynamics. Now, in the case of an air parcel, you have this. This is the energy of an air parcel, and how the energy may change if you change one of the terms, or you perturb that air parcel in a way that you inject more energy or you reduce the energy. So these are the energy terms in an air parcel. So think again about that balloon of kind of like transparent boundaries, if you wish, a thermal of air, as we call it in meteorology, a thermal. So that parcel of air has this energy components that you see here. I will go through in detail, but maybe first for you to understand is these two concepts, diabatic and adiabatic. Adiabatic means that you don't have any exchange of energy from the outside of your parcel of air, right? That exchange of energy from the outside is this. That term in there, the one on the left-hand side. So you can think of it as a kind of like a perturbation. Like you inject energy into your parcel. It could also be releasing energy from the parcel. It can also be negative, right? So that term, if it is equal to zero, we call it an adiabatic process. Adiabatic. And the opposite, when you have actually energy exchange from the outside, we call it diabatic. Okay? All right, so in diabatic processes, this term is not zero, that term there. In adiabatic processes, that term is zero. Okay, good. So let's think of, for instance, a complicated case, and then the other ones will be simpler, in which you have a diabatic process. So you have energy from the outside. Maybe an easy one that you already have been kind of like encountering is you have net radiation. How many times have I said that already? Net radiation here, and then that can be used to vaporize the water or to warm up the land surface and then conduct that heat to the air. So latent heat, sensible heat, warming of the air, and moistening of the air. That moistening and warming of the air is an energy transfer from the outside to the air parcel that is here, right on top of the air. So that's a diabatic process. So you have an energy from the land surface, which is H, and lambda E, which is also energy, latent heat, coming from the land surface into this parcel of air. Now that parcel of air has to kind of like accommodate that energy, because that energy can be destroyed, right? So what does it do? It has three options. The first one, the most intuitive, is increasing temperature. You have latent heat, sensible heat, so you have heat coming, energy coming, it increases its temperature. Okay? That is this. We call it internal energy, usually. Okay? And it's just the specific heat at constant pressure times the change in temperature. That's the amount of energy used to increase the temperature, right? It's kind of like in the latent heat case. You have how much energy it takes to warm up 1 liter or 1 kilogram of air, 1 degree times how many degrees it has been warmed up. And that will give you the total amount of energy that is used to actually increase the temperature that many degrees. Right? Okay. Another option is that you have latent heat happening. That is quite unlikely next to the ground, because what that means is that you have phase changes in the air next to the ground. What can be that phase change? It can be, for instance, you have little droplets of water, liquid water, that get re-vaporized in the air. That's fog, liquid water, right? Fog is a cloud formed next to the ground. So a cloud formed next to the ground, when it receives heat from the surface, it can actually use that energy to vaporize the little droplets of liquid water that it has into vapor. So that would be equivalent to actually using the radiation to vaporize water from the soil, right? It's just using energy for a phase change from liquid to gas. So it's a latent heat flux process. You could also have the opposite, condensation, already here. Let's imagine you have super saturated air in which you have some moisture and heat coming from the land surface, but at the same time you also have condensation happening here, and that would be a release of heat. It won't be an intake of heat, it will be a release of heat. So that will be a different sign in this equation, right? But if you think of this that I mentioned before, okay, what would be the energy used to change the phase of liquid water into vapor? For instance, if you have fog in here and we were warming it, so the energy used will be the amount of energy that it takes to change phase or evaporate 1 kilogram of water times how many kilograms have been evaporated. This is the evaporation. It's just the delta Q. What is Q is the specific humidity. So the change. How much extra vapor we have? Why do we have extra vapor? Because we are vaporizing liquid water. The liquid water is not vapor, it's liquid. So the Q increases when we are vaporizing that fog. The specific humidity, which is only vapor, water vapor, increases, right? So in that sense, you can actually use that energy on the land surface to vaporize the little droplets of water that are in the air next to the ground. And the total amount of energy that you would use for that would be a product of how much it takes to vaporize 1 kilo times how many kilos of extra moisture you suddenly have, so how many you have vaporized. That will be the total energy that you have used. completely equivalent or analogous to how you do it for the sensible heat flux or for the thermal energy, the temperature. Temperature and moisture, again, very similar in this sense. Okay? That will be two ways of using the energy. You can change your temperature or you can vaporize water, the same as the last sentence. With the radiation, you can use your radiation to sensible heat flux or to latent heat flux, right? You can warm up or you can change phase of liquid into vapor. Two options. And as I said before, the change of phase of liquid into vapor takes more energy. So it's a more efficient way of kind of like dissipating extra energy, if you wish, or distributing or partitioning your input energy. Okay? Good. And this in here is the only term that doesn't apply to the surface, which has to do with the pressures, forces. And I'll explain that a little better next, but you may remember maybe from Nico's lectures or somebody else's lectures that the height is a form of energy, it's potential energy. So you have the air at different heights, it implies that it has different energy, and so on. So that's kind of like a potential height, potential energy in some way, but I'll go to that in a second because it actually, when you apply it to an air parcel, it means also something slightly different. So let's keep that on hold for the next slide, and I'm going to explain that a little better. So we go back to the same equation. I didn't change anything. This is the first law of thermodynamics applied to an air parcel. Okay. First possibility for the adiabatic processes. So you have an adiabatic process, meaning this is zero. So we're going to go to easier examples. You have purchased the most complicated ones. Now it's going to be something easier. Now you have this adiabatic process. This means that this is zero. It goes. Now what else goes in here? Well, if it is a dry adiabatic process, it means that there is no moisture that is changing phase. So this is gone. So imagine just air in which it doesn't have any moisture, or the moisture that it has is not changing. There is no phase changing, because if delta Q is zero, this is also gone. I mean, it's not just if you have Q equals zero, but also if delta Q is zero. So you either have no moisture in the air or no changes in moisture. So then you end up with only two terms in that, which are these two in here. One has to be equal to the other, right? So these two have to be equal. Now, what are those two? Now, one is the internal energy, as we call it. It's the temperature, the amount of energy that you can accommodate by increasing your temperature. If you're thinking of like inducing energy into a parcel, how much energy it takes by increasing its temperature. The other one, it relates to the pressure, as I mentioned before. So how is this actually working in nature? Let's think of, for instance, you have your air here next to the ground. It warms up and it moistens through the surface, okay? That's diabatic still. So we have this is not zero at that stage. Okay, now we have moistened and warmed up the air. So what happens? If you increase the temperature of the air, we saw before that the density is decreasing. Density here. So the density of the air, when you warm it up, is decreasing. That's the state law of ideal gases, but it's also pure intuition. So when you warm up the air density decreases and it becomes lighter, right? Also, when you moisten the air, we saw it in one of the first slides, that the air, when it has moisture, it is lighter. So by the latent and sensible heat flux, you're reducing the density of the air. Now, if you reduce the density of the air, what happens? That this term becomes smaller. So what happens? The air wants to move up suddenly. You're creating a positive buoyancy, we call it. So the weight, mass of the air, if you wish, is becoming lower. And since it still wants to go up following pressure gradients, we break the hydrostatic equilibrium and the air starts moving up. positive buoyancy. It's lighter than the air on top, and it moves up. Okay. Now, let's say it moves up without further exchanges of energy from outside, so adiabatically, and it doesn't have phase changes, so dry adiabatic. So what happens with that air? What happens is that as it is moving up, it's generating work in the surroundings because it's expanding. It's moving to lower pressures. So as it moves to lower pressures and starts expanding, it's generating a work in the surroundings. And that takes energy. And that energy, it takes it from its own internal energy, it cools down. So as the air moves up to lower pressures and starts pushing in the air in the neighboring sides, it starts cooling down because it's using its own internal energy to push. That's that equation there. That's exactly what it means. It means that when you move air up and it starts expanding, the energy that it uses to expand and push in the surroundings is coming from its own internal energy. So it's cooling down to provide the energy to push in the surroundings. And that is the reason why it's colder up there than it's here. Nothing else. So when you move into higher pressures, there's lower pressures, higher altitudes, the air will be colder. And that's because that air is actually, as it is lifted, is being cooling by spending its own internal energy. You can also see directly from the state law idea of gases. If you go to lower pressures, the temperature is lower, right? So that is why it's colder when you move up, you go to the mountain, when you just take the plane and you know that outside you have a temperature that's above what we have. Okay. Now, that is the, well, we started with a diabatic process because we had an exchange from the land surface into the parcel here, and then we explained how it works when you have a dry adiabatic ascent in which you don't have further exchanges, so it's adiabatic, and it follows dry, the dry adiabatic ascent because it doesn't have any phase change. So this is also zero. Okay, you can calculate what is the decline in temperature as it moves up. That's what we call the lapse rate. The lapse rate in meteorology is the change in temperature with height. Okay, nothing else. It doesn't need to be meteorology. It can be a lake, for instance, in which you have a vertical temperature simplification. It doesn't matter. So changes in temperature with height in physics are called lapse rates. I don't know why. To be honest, I don't know why. You can calculate it. If you have this equation here, and you substitute this delta P for your hydrostatic equilibrium equation here. So you know that delta P equals this multiplied times the delta theta. Then you can actually work it out. Send the delta theta here so that you can have delta T divided delta theta. So the changes in temperature with height, which we call it tau. So it is this adiabatic lapse rate. It's just this, the change in temperature with height. And you'll see that if you take out the terms that, I mean, it will take you 5 seconds to do it, you get that this is equal to gravity divided by the specific heat of constant pressure of air. And that is 1 degree per 100 meters. How much does it cool as we move up? 1 degree per 100 meters. All right? So the only thing you need to do is take the first thermodynamic law, take out the terms that you don't care about, no exchanges from outside, no phase changes, and then you substitute that from the hydrostatic law, the change in pressure, and you get 1 Kelvin per 100 meters. You can do it at home if you want, but it's straightforward. Okay, so that is the change in temperature with altitude in a normal situation. It's called a light gas. You lose 1 Kelvin every 100 meters that you move up. Okay, good. Now, what about the wet adiabatic case? So in the wet adiabatic case, you cannot throw this out. So wet adiabatic means that there is moisture, and that moisture is changing in phase or in state. It's moving from liquid to gas or gas to liquid or something like that, right? So you have it in here in the equation, and you cannot take it out. It's not equal to 0. So what happens there is that the equation is a little uglier. It just looks like this. It's the same, but you have to term in there. And now we call it the wet adiabatic lapse rate. So one is the dry adiabatic lapse rate, and the other one is the wet adiabatic lapse rate. And that is a little lower. It's between 0.5 or 0.6, okay? Kelvin per 100 meters. So what does that mean? It means that that air that you have here, that you have been moistening and warming from below, and suddenly starts moving up because it becomes lighter and starts putting pressure on the surroundings by using its own temperature. So cooling down as it moves up. At some point, it's been cooled down to a point in which it reaches saturation. Remember the closest Clapeyron law. So there is a point in which that moisture that it has already touches that curve, that exponential curve, because it's cold enough. Then you start having condensation. And because condensation is releasing the amount of energy that had actually been used to vaporize the moisture, you warm up the atmosphere after that. There's an extra energy source out there. So what happens then? The vertical decline in temperature is lower, it's less steep, because you're emitting energy constantly as you're condensing the moisture. So after the point in which the air starts condensing, the temperature with height declines less, because you're emitting that energy that you initially took to vaporize that moisture. That's a latent heat flux. That's why we call it latent heat flux. Until there, the moisture didn't really provide any energy. It was latent. But at the point in which it starts condensing, it starts emitting all that energy that it took. Does that make sense? Okay. So then I think this makes sense now to you, because I essentially explained this already, but maybe we can put a few more things here. Now, there are a few concepts coming, but this process is what we just explained. You have certain air here that is being warmed up and moistened by the soil. So it becomes lighter, it starts moving up and losing temperature because it's pushing the surrounding. Cools down, cools down, cools down up to here. This axis is temperature. Okay? Temperature, altitude. So this is the lapse rate. And if you take calculate your Pythagoras thing and your slope, you will work out that this is actually then 1 Kelvin per 100 years, right? Okay. So at this point that we call lifting condensation level is when the water starts to condense. It's cold enough, it starts to condense. Okay. Good. And after there, the temperature starts increasing less deeply, right? Like 0.5, 0.6 degrees per 100 meters. So this is the dry adiabatic lapse rate. And from here, it moves through the wet adiabatic lapse rate. And that's even if the air here had moisture. So essentially, the air, when it has moisture here, but it's not experiencing moisture-based changes, it moves through the dry adiabatic lapse rate until that moisture condenses. So you don't need to have pure dry air, 0% moisture for this to happen. You need to have no phase changes. So there is no condensation yet. At the point in which you reach your lifting condensation level, starts to condensate and then release energy, and then it cools down less than before. Now, why is it 0.5, 0.6 degrees Celsius and not just the constant like for the dry? Because it depends on how much moisture you condense, right? If you look at the equation that we had before, well, you can see that depending on how much moisture you manage to condense, you will have more or less energy being released. And if you condense a lot of moisture, then you warm up a lot of the atmosphere, and you will have a lower or less steep decline with height of your temperature. So that actually explains why this is not linear. Here maybe it's like 0.4, and then here it turns to 0.7, because here it's condensing a lot more moisture. This is a cloud base, of course, bigger. point in which you reach saturation, you condense a lot of moisture. And then as it keeps moving up and cooling down further, there is less and less condensation until you reach to the point of the top of the cloud. And of course, then this resembles a lot more the dry adiabatic lapse rate because it has lost all the moisture. All right? So that explains kind of like that shape of curve that you see there. So we call it lifting condensation level to the point in which it starts condensing. That's an important concept. And now we turn to something that is super important for you to understand, and I hope that I do a decent job at explaining, which is the concept of potential temperature. Now, potential temperature is the temperature that the air at any height in the atmosphere would have if you were to bring that air down to the land surface through the dry adiabatic land stream. So if you bring it down, what would be the temperature? So if you take this air here, you bring it down, perfectly dry adiabatically, essentially bring it down, then you get to the surface level and it has 20 degrees. Okay, so that 20 degrees is the potential temperature of that air, 20 degrees. So the actual temperature that it has is 10 degrees, but the potential temperature is 20 degrees. If you wish, is a temperature correcting for the pressure differences in height. Okay, that's what the potential temperature is. It's a temperature in which you correct for the pressure change. So if it has very low pressure, then you know that that low temperature in reality and potential temperature will be high. Okay? So think of taking that parcel back to the surface, what will be the temperature that it will have? That's your potential temperature. Temperature corrected by pressure. You can also correct your temperature by the humidity that it has. Why does it even matter? Why would you actually correct by the moisture content of the air? Because of what we mentioned earlier in the lecture, that the moisture content also changes the density of the air and also affects the ascent of the parcel and so on. That's a very small correction. This one here, and you can see actually that there is almost no change, but it's important to consider that correction as well. So if you can correct your temperature by the pressure, you get the potential temperature. If you correct your temperature by the pressure and the humidity content, you get your virtual potential temperature. That is almost the same as the potential temperature, but it's important for you to know why we call it virtual potential temperature is just because it's being corrected by the moisture content the air has. So we correct for the pressure and we correct for the moisture content. Now, why is that we do all that? Why do we want to know the virtual potential temperature and we don't get just the normal temperature and that's fine? Because we want to know actually what would be the behavior of that parcel of air that you have here when it's up there. And I'll explain that a bit better because it affects very much the stability and or instability of the atmosphere, whether the atmosphere is going to tend to pull out the air and so on, or if that air parcel is not going to tend to move out. So let's go one step back because I'll probably have to explain one thing first. Now, you have your virtual potential temperature. If you have a perfectly dry adiabatic case, like this one, the virtual potential temperature is just a vertical line. So everything in that vertical is the same virtual potential temperature, right? So if this atmosphere was actually just following a perfect dry adiabatic lapse rate in which the air on top is just exactly 1 degree less per 100 meters, it will all have the same virtual potential temperature. You bring that air to the surface and it has exactly the same temperature. That has to do mostly with the correction of pressure, but as I said, we also do a correction for moisture as well, called virtual potential temperature. Maybe for simplicity, we can think of potential temperature, but it's true that there is a little change. So let's just think about that. If the air was stratified in the atmosphere perfectly according to the lapse rate, dry adiabatic lapse rate, all that air will have the same virtual potential temperature. All right. Okay, let's keep that in mind for a second. We'll get back to that in the next, so the following slide, because we use that concept to determine whether the atmosphere is stable or unstable. Because if the air has a higher potential temperature than the air on top, it'll tend to move up because it's lighter. So it's not, what matters is not the temperature relative to the air on top, the actual temperature, but the virtual potential temperature, because that air on top has a different pressure and maybe humidity content. And that's why we're doing this correction, because you want to know how your air parcel is going to behave with respect to the others. It's going to move up. And that depends not only on its temperature, but also the temperature of the other and the pressure of the two. And that's why we correct for that pressure to know whether it will tend or not tend to move up in the atmosphere. And that will determine whether you have a stable atmosphere or an unstable atmosphere, whether you're going to have clouds and rain or not. Okay? So the stability of the atmosphere is diagnosed with this virtual potential temperature. You'll see that in 2 slides, but just for you to know why we're actually putting emphasis on understanding this concept. Now, just a couple of further things that I need to understand before we move into the stability, which is the last thing that today we really need to make it clear, actually. Okay, so we have the environmental luxury. What is that? It's the actual. Maybe today you move up, you launch a balloon with a thermometer, and it doesn't measure exactly 1 Kelvin per 100 meters. Because that depends on other factors. It depends on the anticyclonic conditions, fronts, it depends on larger scale properties, it depends on other things, right? So we know that the air that moves up is going to follow actually the dry adiabatic lapse rate. But the air that is already there may have a different lapse rate. Maybe maybe decreasing in temperature with height more or less than what is the optimum theoretical that a parcel that is being warmed up here will follow. Okay? So that air parcel that is being lifted here does follow the dry adiabatic lapse rate. That, yes, but maybe the atmosphere around it is not. Right? Maybe it's not exactly the dry adiabatic lapse rate, because the atmosphere was already there. It's the background atmosphere that moving parcel through the dry adiabatic lapse rate is being exposed to. All right? It's not like the background atmosphere. We call that the environmental lapse rate, real, actual lapse rate. This is the real one that occurs. The parcel that lives will follow the theoretical. Still, if it is an adiabatic process and so on, will follow 1 degree per 100 meters. And it's crucial to compare that to the environmental, the real one, to know whether it's going to be colder or warmer than the surrounding in potential temperature terms. Because that will determine whether the parcel stays or continues moving. And that's stability or instability, all right, or instability. So that's why it's so crucial. So when we think about whether the atmosphere is stable or unstable, we have to think of whether that parcel that is going to move through the dry adiabatic lapse rate is going to find itself surrounded by air that is lighter or is warmer, or is lighter or is denser or heavier. So whether it's warmer or is colder in terms of potential temperatures. That surrounding air and how it changes in temperature with height is the environmental lapse rate. And here I drew it with this green thing, okay? So that's an example environmental lapse rate. It's not a theoretical line. Will change every day from region to region. But imagine this case in which you have an environmental lapse rate that looks like this, okay? Well, this parcel that you're moving up with the dry adiabatic lapse rate, which is where it will move up, and it is not theoretical, it's true. You leave a parcel move up, and if it doesn't have exchanges with the outside, it will lose 1 Kelvin per 100 meters. So it will move like this. But we don't know if the atmosphere in which it's moving is actually having a stronger or lower lapse rate. So if it is cooling more with height or less with height. And that's what we need to compare to know the stability of the atmosphere. So let's say it's, for instance, we have this parcel that lives up to 500 meters. Now, how is the atmosphere surrounding it? Well, it's actually warmer. So if it is warmer, it implies that that parcel is going to be heavier than the surrounding atmosphere. So most likely it's not going to move up any longer. It's going to stay there. You're suppressing the convection. You're making the atmosphere stable. You're not favoring mixing. All right? So that is a case of stability, if you wish, in which you have your environmental lapse rate being implying warmer temperatures than the parcel that moves up. So implying that the parcel that moves up is going to be denser than the surrounding. So it's not going to tend to keep on moving up, right? Surrounding and on top, right? So that is a case of stability. We'll go to that in a second, but it's important that you start understanding a bit how you can diagnose the stability in the atmosphere. Okay? So in this example that I put as the environmental lapse rate, that parcel that starts ascending, that will always ascend through the dry adiabatic lapse rate as long as the process is adiabatic, there is a point in which it will find itself being a lot colder than the surroundings and the air on top, and therefore the buoyancy will be negative. So therefore it won't tend to be back because it's denser. Okay? So that's one thing that we have to remember. But let's keep in mind that it keeps moving up. Why would it be actually moving up? There is one possibility. We said that there are two ways in which you can actually induce mixing of the atmospheric boundary layer. One is to warming it and moistening the air, right? Which induces that air is going to be lighter and then to move up as we just saw. And the other one is through roughness and mechanical friction and essentially getting all that wind, horizontal wind coming, being broken by the trees and the roughness of the buildings, and then being lifted up through pressure changes. So if that was the reason why that parcel started moving up, it is possible that it still has some momentum and keeps on moving up, let's say, even if the air surrounding it is still lighter, right? So let's think that the parcel keeps moving up. It keeps moving up until a point that is the lifting condensation level, right? That we know. Lifting condensation level starts to condense, so it starts moving up through the wet adiabatic lapse rate, all right? There is a point in which it crosses the environmental lapse rate. Why? Because environmental lapse rate suddenly, for whatever reason, is steeper here. And then because the heating of condensation, that parcel of air is suddenly cooling down less with height than it would otherwise. So at some point, it finds itself being actually as warm as the environment in which it is, and suddenly even warmer than the environment. At that point, that parcel of air is shot up, and that's actually what generates convective clouds, right? And suddenly you have the air being substantially warmer than the surrounding air. Then it moves up through the same trajectory that it would move anyway, but much faster. It moves faster because it's energized by the fact that the air that surrounds it is a lot denser, heavier than itself. So when it has a higher temperature than the surrounding air, it just gets shot up and you form like super big clouds, convective clouds, thunderstorms and stuff, right? And all that, as I say, depends on this green line in here, which we call the environmental lapse rate. It changes from one day to the other. It depends on the large scales, synoptic conditions, the weather at the large scale, and so on. What does not depend on that is this red line. This red line is perfectly theoretical. It's just thermophysics. It's just how the parcel actually declines in temperature and height. And that's what it is. So you have to compare the two to know whether that parcel that's ascending will actually be warmer or colder than the surroundings, which will determine whether it keeps on moving up or it actually stays or stays. We'll get to that in a second again. But this is the probably most important, most difficult concept that you're going to hear today. So it's important that we get through a bit slower. I know I'll ask if you have any questions, but Okay, so the point in which the parcel actually is at the same temperature as the environmental lapse rate, we call it the level of free convection, because from that point onwards, you have free convection. You have that parcel of air being shot up at super high speed, forming a massive cloud, until the point in which they cross again, which is what we call the equilibrium level, which is when the cloud top, usually you see the cloud top. So essentially from the cloud base to the cloud top, what you see the region in which the temperature of the environment is actually colder than the temperature of the rising air, because that would imply that you have a very explosive convection, in which the air suddenly gets shot into high up the troposphere. Okay, so that's what I'm trying to explain here. So yeah, go ahead.
My question is, why is the latent released in the exactly in the release?
Where is it released?
So we are in the Ghent region.
Yes.
Why is the latent release?
So the latent heat release happens here because it's when condensation happens, right? Condensation happens there because you reach this point of condensation in which you have cooled down your air to the point in which you reach that Clausius-Clapeyron equation, right? And from then onwards, you start having a release of latent heat because you're still cooling the air. I mean, this is natural temperature is still cooling down. So even if it is warmer than its surroundings, it's still colder than before compared to its own humidity content. It implies that it still will condense more and more.
But the release of latent heat has something to do with the environmental lapse rate.
Well, it will warm up the environment if you have actually that release being diabatic. So if you actually have that release being exported outside the parcel, it will warm up the surroundings. If you have that release actually just being contained within the parcel, it will just increase the temperature of that parcel. Could be the temperature, or it will just imply that the temperature declines less fast than it would otherwise without that extra release of energy from the condensation. Yeah. Any other question? Yes.
Also one of the environments that is one of the environment and the parcel of air is the same rate.
So so when you have the parcel of air is a very theoretical concept. In reality, you do have thermals of air moving up, which are very vague. But most of how the atmospheric boundary layer works is the plumes are very diffuse. Did you see the video that I put the other day where it looks like fire moving up and so on? That's actually more like it actually works in nature. So if you have those kind of like flames of fire moving up, what happens is that the moment in which it starts condensing, part of the energy that is released will be going to warm up that particular moving upwards air, and part of it will be actually exported to the surroundings. So it's just diffusing that energy and moving it through convection around. So it's not that the energy is encapsulated within the moving parcel, but part of it will be diabatic, part of it will be exported to the outside. So it's kind of like the parcel of air is a very convenient way of visualizing this. But in reality, the air moves in a fashion that is much more in the direction of mixing with the surroundings and transferring energy in a diabatic way from the surroundings in and out. Yeah.
Because the environmental last year that becomes warmer again at greater heights. Because of
this curve in here, well, it is probably affected. I mean, I put that curve out of the blue. In reality, it doesn't need to look like this green line. It's an example environmental lapse rate. You can take another thing. But part of the reason why the atmosphere in total warms up is indeed the release of heat through condensation at the height. So usually you do have at the height of clouds a warmer atmosphere when you do have those clouds than if you didn't, and that has to do with the release of heat through condensation. Yeah. It's still cold enough to have ice in the clouds. So this is actual temperature. So again, we're thinking here, well, in this case, you won't have ice because you're talking about 5 degrees temperature. But in other cases, you would actually have much higher altitudes in which ice will be generated when you have that condensation. And especially in the top of the clouds, you will have mostly the water in the form of ice. Despite the fact that, of course, forming the ice releases a lot of energy, but just the temperature and the pressure is so low, and the temperature is so low that you still have ice. Any other question? So, same. This is a case of a stable atmosphere. Why is it stable? It's stable because the air parcel, as it moves up through the dry adiabatic lab stream, it will find itself colder than the surroundings, so heavier. So it won't try to actually move up much. And if it doesn't move up much, it doesn't mix up much, that's what we call stable. You won't have clouds forming, and so on. It will be stratified like a lake, perfect stratification. The Earth has been warmed up, doesn't get warm up enough to actually find itself in its essence warmer than the surroundings. It will still be colder than the surroundings, and therefore that upward motion will be inhibited. You will have what we call negative buoyancy, stability. If you look in terms of temperature, that looks like that. But if you look in terms of virtual potential temperature, and that's the reason why we use it, it looks like this, which is a lot easier. That line, that perfectly vertical line, is a neutral atmosphere, meaning that as the atmosphere, as the air bubble, if you wish, starts moving up through the dry adiabatic substrate, it encounters an environmental substrate that is equal to its temperature. The environmental substrate is exactly the dry adiabatic substrate. That is the neutral atmosphere. Not stable, not unstable, neutral. And that's this. That's vertical line, meaning the entire atmosphere, the atmospheric environmental substrate, so the real one, is just same virtual potential atmosphere temperature all the way through. So when you move a parcel out, it will find itself at the same temperature as the surrounding. Okay. Now, if what we find is this, so that the temperature actually is higher. This is the environmental temperature. The actual temperature change with height. If the actual temperature change with height implies that the temperature is warmer in virtual potential temperature terms, as we move out, the atmosphere is stable because the air parcel that moves up, it moves up to this vertical line, the dry adiabatic substrate of constant virtual potential temperature. So it will find itself being colder than the environmental temperature. And if it's colder, it implies it's denser, it will be neutral, it will be stable. So if the change in temperature with height is like this, implying the virtual potential temperature is actually increasing with height, or the same like this is the same thing but plotted correcting for the pressure, right? And humidity. So essentially, if you think of actual temperature, if it is easier for you, the environmental substrate actually implies that as you move up, you lose less than 1 degree Kelvin per 100 meters. So you're still cooling down in real actual temperature terms. But you're warming up in terms of virtual potential temperature. Because virtual potential temperature is 1 kilogram per 100 meters. It's the dry adiabatic substrate. right? So if you move up and you're losing less than 1 Kelvin per 100 meters, that implies that you're increasing the virtual potential temperature behind. That's a stable atmosphere. Why? Because the parcel that moves up from here, it will move through 1 Kelvin per 100 meters. So it will find itself being colder than the air surrounding it. So it won't keep on going up. It will be denser than the air that surrounds it. So it won't be moving up. It will just further ascend and then stay. Stable atmosphere. It doesn't generate mixing. It doesn't create cooling of the air that forms clouds and rainfall. Nothing. Stable. Clear skies, nice weather, perfect to go to the beach. So, okay, that's an atmosphere in which the temperature declines less than 1 Kelvin per 100 meters. Or in other words, a temperature in which the virtual potential, an atmosphere in which the virtual potential temperature increases. And you can see now why we actually have the virtual potential temperature definition, because it's easier to correct for the pressure and so on, because then we can think that anything that has a virtual potential temperature that increases is going to be stable. And of course, the opposite. If you have the situation in which you have the virtual potential temperature decreasing with height, then you have an unstable atmosphere. What does that mean? That you're using more than 1 Kelvin per 100 meters. So that the parcel that moves up through 1 Kelvin per 100 meters will find itself actually being warmer than the surroundings and being pulled up. And then it generates clouds, and then it generates rainfall, mixing, and then the air goes down, picks up new air from the bottom, and you have essentially the figure that you saw the other day. The video that you saw the other day, that's a classical mixing of the atmospheric boundary layer when you have instability. Right? This is a typical thing that then when you go home, you read it. Yeah, I actually read it. But if you want, I can give it another shot and see if I can make it even worse. But I think for some of you it turned out clear, but yeah. Any question? Okay. So let's put a couple of examples. So imagine you have a super dry ecosystem like the desert, for instance. Well, what will happen? You have radiation coming in from the sun. You will also have quite a lot of albedo because the desert is pretty bright, so you have a lot of reflection of that. But well, let's imagine that in total you have a high net radiation. That net radiation will be mostly used in sensible heat flux because you don't have moisture in there to evaporate. So you have very dry air, very high sensible heat flux. So that dry air, the way that sensible heat flux is actually generated is that you have the radiation warming up the land surface, the pores of the soil and so on. And that high temperature of the soil is conducted to the thin layer of air on top because the temperature of the thin layer of air is lower than the temperature of the soil that is being heated by the sun. Right? So you have a gradient of temperature from the warm soil to the slightly colder atmosphere. So then that implies that there is a conduction of heat. All right? Following that gradient, at that point, that air next to the ground has become warmer and therefore has become lighter, and it tends to move up through the dry adiabatic lapse rate. So it's losing 1 degree temperature every 100 meters. Why is it losing temperature? Because it's expanding, it's exerting workings around it. Keeps on moving and it moves up and it's gone. I mean, it won't form clouds because it doesn't have any moisture. Sorry, no? That's it. We can actually see what happens with that air layer, which will, of course, will be bouncing back when it cools enough. Because it won't keep on moving into the troposphere. The air doesn't escape easily the atmospheric boundary layer. This is being actually we'll see that in the next lecture. But yes, essentially that air will just continue to move up until it cools enough so that the temperature of the air surrounding it is equal to itself, and then stays there or it sinks down. So, okay, but it won't form clouds because it doesn't have any moisture because there was no evaporation at the ground. You can have the opposite situation in which you have plenty of vegetation taking water from the roots and so on, and evaporation happening. So in that case, of course, you have the latent heat flux being much larger than the sensible heat flux. Usually it's about 70% of the net radiation, 60%, 70% is used for the latent heat flux if you have sufficient moisture to evaporate. So if you are overcritical to moisture, especially if you have plants that actually tend to get water from deeper in the ground where moisture is more accessible and so on. So you have that net radiation being preferentially used to evaporate water, most of it through transpiration, most likely, if you have vegetation. So you're moistening the air and warming the air because you still have some sensible heat flux, like 20-30% of the net radiation. So you're both moistening and warming, so you're reducing the density. You reduce the density of air more by warming it than by moistening. But we also saw that by moistening, you are also reducing the density, right? So that air moves up through the dry adiabatic substrate because it's still not experiencing phase changes within the air. It's not condensing yet. It's not re-evaporating water. It's just moving up because it has become lighter, and at some point it will be cooled down to the point in which it starts condensing. And then it starts emitting that energy of condensation. And then after that, it moves up, but it loses temperature less steeply than before because it's emitting the energy of condensation, right? So it starts to cool down less than it would have cooled down through the dry adiabatic glacier. Okay, and in that case, yes, of course, you have clouds forming, you have rainfall, and so on. And those two cases are cases in which you have certain instability of the atmosphere, because if the atmosphere is very stable and you have an environmental lapse rate that is preventing that buoyancy to occur, then unless you have a strong roughness mechanical friction, that air won't go up at all. Right? So yeah. Of course, in a desert, you're warming up the air so much from the bottom with sensible heat flux that even if you have a stable atmosphere, you still tend to have some mixing because that air will be super warm, so it just tends to go up. At some point, of course, the temperature will cool down to the environmental lapse rate and then it'll stop. That's a typical situation. Okay, and of course, in that sense, you can see how having moisture in the ground or not having moisture in the ground, having vegetation being active, wanting to photosynthesize, take CO2 and lose water, is crucial for the atmospheric dynamics. Because you can link anything in this sense. You can think of what happens if plants are experiencing a beetle plague or something like that. They are just being eaten by beetles and they don't want to photosynthesize because they are just dying. What will happen? Well, they won't open the stomata to take CO2, of course. That would be absurd because if they take the CO2, it's not being consumed. So why would you open the stomata? The CO2 comes in, then there is no gradient of CO2 from the atmosphere to the inside because I'm not consuming the CO2 that I have taken, so it's not going to keep on coming. So why would I actually lose water? They just don't open the stomata. If they don't consume the CO2, they won't photosynthesize and open the stomata. So if they are being eaten by beetles, let's say that ecosystem won't be opening the stomata to photosynthesize, so it won't be losing moisture through latent heat flux, so it will look a lot more like that and less like this. It won't be generating convection forming clouds and rainfall because it will affect the entire dynamics of the atmosphere on there. So not just about the moisture content of the atmosphere, it's also how the atmosphere responds to being differentially warmed or moisture from the bottom. And that depends on whether the vegetation wants to photosynthesize or not. It depends on how much moisture we have over or below the critical moisture. Right? So the effect of the land extends all the way up to the top of the clouds. Right? Okay. So, any question? We're just 5 minutes away from finishing the work. But, then. So this is the classical partial lifting that I mentioned before, in which you have a thermal, in which you have sun radiation coming in, you moisten, you warm the air, and then it moves up through the dry adiabatic glacier. And then if you have some moisture, it will form clouds and so on. So that's the typical way in which you raise air. That's what we call the positive buoyancy, and it's just through sensible and latent heat flux. We also said that, I actually didn't mention this, there's another way in which you can move air as neither friction nor warming, which is a convergence. Like we talked about the other day for the forest and so on, in which you have a lot of air coming, maybe from different directions, and as it comes, the air lifts up because of convergence of positive pressure, right? And that will generate a negative pressure in the bottom because you're essentially emptying the atmosphere here because the air is coming, and that will generate a negative pressure here. So it's a convergence and divergence. When you have convergence, you usually have divergence somewhere else because it's the fluid, right? You have more pressure here, somewhere else it must be a negative pressure. Divergence, convergence. So that's one way of lifting air, that you have air coming from different directions, and suddenly you have to move up that air because there is a positive pressure gradient, and so on. So that's actually another way you can have vertical motions of air. It's not the most typical. The most typical is the thermal lifting, especially what happens, for instance, in the summer when you have thunderstorms. It's really air warmed up by the land side because that moves out because it's lighter. That's a classical situation. This convergence happens more, for instance, in the case of forests, we mentioned the other day, in which you have air coming and then it's slowed down by the forest. So you have a convergence, you have a traffic jam, and then the air moves up. That's a case of convergence. Orographic lifting is another way, but I think this is something that was taken for granted, that you know, or you have heard of. When you have a mountain, the air comes, and of course it has to go up. What else? It's not going to cross through the mountain. It's a tunnel. So it has to move up, and as it moves up, of course, it gets pulled down because it's moving up to lower pressures, right? So forms clouds, eventually leads to rain, and then the air keeps going to the other side of the mountain, and because it has lost the moisture, typically never rains there, and you have what we call the desert on the leeward side of the mountain. All right, so that's another way of lifting air, to have actually a mountain that forces the air to move back when it hits in that direction, right? And of course, the air, as it hits the mountain, it starts moving up to lower pressures following a dry adiabatic glacier, just like any other uplift of air. And that's why it cools down, and that's why it's colder in mountains. And the fourth way of actually generating upwind motions is the frontal wedging. And this is more like for Hans Revie to explain next year, because it's more like regional large-scale meteorology. But this is how fronts is actually typically formed, in which you have cold air, and then you have moving air that is warmer on top, as you can see here. And they don't mix because there is a thermocline here, so this air is denser, it's cold, and then as it moves here, it's different. That's a classical front situation. That's more for meteorology, less to do with the content of this course. But in essence, these are all combinations of either warming and moistening from below, or roughness, or just simply having obstacles that force the air to move out. And this is something that I actually mentioned the other day when I put this figure, which is that when you have partial uplift somewhere, for instance, through this thermal process in which you warm and moisten the air from below, there is air coming from the sides, right? To fill in that gap. There's a kind of like air leaving here, so you have to actually fill in that gap a negative pressure. A negative, I mean, if you want to think in terms of physics, that air that is being warmed up and moistened is actually leaving. And as it leaves, it generates a low pressure here. And because winds form as a gradient pressure, force, so essentially the winds move the air from regions in which you have high pressure to low pressure. This is a gradient of pressure. So if you're generating a gradient of pressure here, by moving the air that's moving up, then of course the air from the side is moved to here. So winds come to here. And that air from the side can be actually quite moist if you're in a coastal region, for instance. That's what happens when you have, you're in a stand, for instance, in summer, and at 6 in the afternoon, you see these massive clouds forming. That's essentially that process. So you have, during the day, the land is warming up faster than the ocean. That has to do with the thermal properties of water. In the ocean, most of the water is just water, so it takes a lot of energy to warm it up. So it warms up less. The specific heat of water is very high. And in addition, you have currents that mix with water. So in essence, the temperature of the ocean is going to change a lot less than our land, where not only you have also other materials that have lower specific heat capacity, so they actually warm us faster, but also you don't have that power to convect that energy as in the ocean. So the surface keeps on warming faster during the day because of the sun radiation in the ocean. And what happens is that the air on top will also be warmer through sensible heat flux. So the air starts moving up more than it does in the ocean. So what happens is that the ocean air rather moves towards the coast, filling that gap. And then, as it moves to the land, it gets warmed up by the sensible heat flux. So you have suddenly warm and moist air, because that's moisture that was coming from the ocean, being lifted, and in that case, you can form very big thunderstorms. So you're essentially moving all the air from the ocean, warming it up by energizing it through the continent, and then that air that is moist and wet moves up and forms thunderstorms in the coast. That's a typical process that you find in the coast, and it is at a different scale the same process that you find in a monsoon. A monsoon is exactly that. You have the continent warming faster than the land, than the ocean, especially at certain seasons of the year. So you have this season of the year, the ocean tends to be colder and the land tends to be warmer, and therefore what happens is that the air over the land moves up, the air from the ocean comes in to fill in the gap with all the moisture, and then as it is being warmed up, it lifts, and then it forms super big storms as well. So as the rainy season in the monsoon is actually formed that way. Okay? And it's the same process again that I mentioned the other day, in which you can actually get to have more rain when the soil is dry. That was a quiz question the other day. If you have dry soils, sometimes what happens is that you have more sensible heat, so the air gets warmer, moves up, and then the surrounding air comes in with moisture. And then as it moves up, you get a cloud and rain here. So essentially withdrawing the moisture from the surroundings and lifting it up through the sensible heat because the soil is dry, right? So that's why you sometimes get a negative feedback, implying if it rains less and the soil gets drier, it will rain more. So that's a negative feedback. That's essentially implying that you're buffering the initial change instead of amplifying it as in a positive feedback. So the soil moisture precipitation feedback can be positive when you have more soil moisture, more water to evaporate, more rain, or negative when you have less moisture, but then more convection, and then more rain because you withdraw the rain from the side. Okay, we're getting that. Any question? No? Okay, so you may expect fewer clouds to form over forests because trees take water from the atmosphere with their leaves. Clouds only form downwind from forests. Trees emit particles that inhibit cloud formation. God admires the beauty of forests from up in heaven, and you expect more clouds, not less clouds. Diego, stop trying to confuse it. So, A, who goes for trees take water from the atmosphere with their leaves? No? No one? B, no, the water is taken from the roots. 99.99. Clouds only form downwind from forests. That's not reasonable. Trees emit particles that inhibit cloud formation. Actually, it's the opposite. We got the other day that there are certain forests, like conifer forests, that actually emit these particles that can form clouds because the droplets are here on top of on the surroundings of them. Now, God admires the beauty of forests from up in heaven. Yes. Very good place. Do you expect more clouds? Some of you that can raise a hand. That's good. Yeah. Let me say why the right answer is E and not C, actually, not D. So it definitely matters where clouds are formed. So the answer B is absolutely not nonsense. So yeah, the clouds may form not only from forests, but if you have big forests in the south, for instance, you have big Amazon, you have a lot of clouds actually forming still within the same forest. Of course, they travel. I think we talked the other day about the fact that the effect actually for temperature is a lot more local, which is totally true. For temperature, when you have the energy partition working for instance, you have more transpiration for different trees, you have lower temperature because it's using the energy that otherwise would go to sensible heat flux. That is local. So you have trees affecting temperature locally. Cloud formation and rainfall, the effect of that they have is a lot less local. It's a lot more remote. It's really a downwind effect. But of course, if you have a forest, that downwind may still be within the forest. So you still have many times that those clouds and rain that are generated by the forest is still happening within the forest, as in the case of the Amazon, right? In the Amazon, you have about, if I recall correctly, about 40% of the rain in the Amazon comes from the Amazon transpiration, for instance. No, you expect more clouds, and you expect more clouds because of this cloud-emitting nuclei that we mentioned. That's one factor, but not the most important. Most important is the transpiration. And they are all. And you'll see that actually in one of the papers that we have in the scientific articles folder in UFRA, which is this one from Ria and Tilly, in which you would actually get the different processes that you have actually all studied, and we kind of like revisited them during the first lecture. So I think it's probably not the most challenging article for you to pick. Last thing that I want to mention, I'm not going to get in depth into this, which is what a balloon sounding is. Balloon soundings are actually used to measure the stratification of the atmosphere. In every single meteorological institute in the world, you usually have 2 launches per day of balloons. You have at 12 a.m. and p.m. UTC, not local time. So there are places in which you have to wake up at 4 in the morning to go launch your balloon. Places like here, in which we're lucky enough that it happens to be not too bad time. But it's actually UTC time 12 morning and evening or whatever that falls. So this actually, maybe I can put this video. I'm not sure if this is going to work. Maybe it doesn't. Maybe it does. So that's here in KMI, so in the Observatoire, the Sterrenbach, yeah? Sterrenbach? Sterrenbach, easy, right? The Sterrenbach in Brussels. So this is Newfield, like 200 meters from my house. And they do this twice a day, which looks pretty miserable, especially when it's windy. And they are launching these balloons, helium or whatever, all the gas that actually goes there. And they actually form all these, yes. See again? If I can lower it, yes. Let me see if I know how to, yeah, it works from here. So essentially they launch this with equipment, as you can see here. And that equipment includes thermometers, it includes stuff to measure pressure, humidity, and weight, essentially. Do we want to see this? Probably not. So the that is done twice a day, and it's to actually measure the acidification of the atmosphere. What do they use it for? Well, to know if the atmosphere is stable or unstable, but also to improve their forecasts, right? They have their models that they can actually use to forecast the weather tomorrow, so they can actually correct the situation for today to have a better forecast of tomorrow. I'm not sure if this actually is still working somehow. Nice. Sorry about it. So they launched the equipment twice a day, all these sensors to measure actually how the state and properties of the atmosphere change in the vertical. They usually launch it with a GPS system so they can recover something when it eventually falls somewhere, as it happens to fall somewhere. I'm sure why there are no more incidents of people getting a sensor on their heads, because there are balloons launched every day. That little thing in there that you see in red is a parachute. So, and essentially what we do that with that information layer is filling these graphs that we call spew temperature log pressure diagrams, where you can put your measurements. I mean, I'm not going to go through this because it's a little complex, but essentially you can fill in your measurements in here, and it'll tell you whether the atmosphere tends to stability or instability, right? And that information then you modify in your climate model, or actually your weather prediction model for tomorrow, so that you can make a better initialization of your model and predict your weather better in the following days. So that is done by all the meteorological institutes in the world. So, any question? Yes. Mm-hmm. So the answer is that the forests generate more clouds, not less. Part of those clouds, they are actually traveling, of course, downwind. But part of the clouds, if the forest is sufficiently big, will actually already affect the forest, will be within the forest. And in fact, that depends not just on the size of the forest, but the strength of the convection. If you have a forest like the Amazon, in which you have a lot of net radiation coming, a lot of transpiration, a lot of warming, then of course those clouds will form almost immediately on top of the trees that have generated them, because there is very powerful convection. We warm the air very much and it moves up. Okay? All right. So specific and latent heat, right? So the lambda and the C, very important. So how much energy it takes to warm up, or how much energy it takes to evaporate. Dalton's law, that is the law of the partial pressure. So you can actually think of the air as a mixture of gases, and the air pressure is the summation of the pressures of the individual gases. Okay, Clausius-Clapeyron law, super important. This exponential curve that shows you where the saturation point is, and there we saw the vapor pressure deficit. We saw the dew point temperature and a few other things. Hydrostatic law, which is that one there, essentially telling you how the atmosphere would be if we are not perturbing it. It's a balance of the weight and the pressure towards pointing up. The law of ideal gases, so how the pressure, temperature, and volume change in relation to each other. Law of thermodynamics, the first one, conservation of energy, which is very related to the previous two. So you can actually understand, if you understand that, how the ascent of a parcel will be in the atmosphere and how the exerting work by cooling down and so on. Potential temperature, and actually virtual potential temperature will be better. Potential temperature corrects for the pressure changes in height. Virtual is also correcting for the humidity changes. And that virtual potential temperature is what we use to diagnose stability in the atmosphere, right? Adiabatic lapse rate, so essentially the dry adiabatic is how the parcel of air will move through as it is lifted and cools down. So that's about 1 Kelvin per 100 meters. And then the wet adiabatic happens when that parcel starts to condense the moisture. And that's less steep, like 0.5, 0.6, depending on how much moisture that parcel of air contains. It's Stability of the atmosphere, remember stable and stable, dependent on the environmental lapse rate, so the real actual lapse rate that we have. Convection and advection, and mention advection, what it is, but it's a horizontal movement, usually we call it advection. It's a bit more complex because it implies a divergence and conversion, so it's not just a flow. But advection usually is used in physics for horizontal movements, as opposed to convection that is vertical. It could be anything in reality. But advection, very much in environmental sciences, when we talk about moisture advection or heat advection, we mean the horizontal movement of air with moisture heat. Right? Mesoscale breeze, that is what we mentioned about Stendhal, or I don't know what city I mentioned, but essentially that, in which you have a cell of convection generated through the fact that you have a differential warming of the land surface in two places. Usually it could be the ocean and land, for instance. And then you have the balloon soundings that I just showed you, just for you to put a bit in context what you saw during the lecture. Still alive? Next lecture is not easier. I mean, I don't mean that this was difficult, but it was maybe less familiar than other lectures to you. Next lecture is probably equally unfamiliar and a bit more difficult. But then things will start to get a little more down to earth and relatable. Okay?